Hi guys, it's Friday and I'm at my conference. In my place, I've left this video, well, it's not really a video, it's just a PowerPoint with a voiceover that will explain how to do these phase diagram problems. Now, this part 1 is only going to go over the stuff that I've already talked about on Wednesday. Here's the first diagram. This is the exact diagram that appears on the handout that I gave you. The first thing that we have to do is figure out what the composition is of the sample in question. Here is the sample. It intersects the number 20. So we know that it's going to be 20% of something. It's 20% of B. And the way that you can verify that is to note that the 100, in other words, 100% of, is over the B. If these numbers were flip-flopped so that the 100 was over the A, then the numbers would refer to A. If there are no numbers at all, and some students have said that they actually find that easier, then what you do, I lost the cursor there for a minute, what you do is you take a ruler and you measure the line AB. Measure it in millimeters. Then you measure the segment AZ. I'm assuming that this line is called Z. AZ divided by AB times 100 gives you the percentage of, right, B. If, on the other hand, you took ZB and divided it by AB, it would give you the percentage of A. All right, now that we know that we've got 20% of B, let's look at the rest of the diagram. Up at the top, in the white region, we have all melt. The line that separates the white from the colored regions is the liquidus. In the yellow region, we have melt plus crystals of A. In the green region, we have melt plus crystals of B. The solidus is the line that separates the yellow and green from the blue. The blue is crystals of A and B. There is no melt there. Notice that the axis has the temperature. The y-axis has the temperature. It's in degrees. So how do we go about reading this? All right, let's say we start with a melt of composition Z and we cool it. We would have to cool it to this point to get any crystals to form. And the crystals that would form at that point would be crystals of A. There's two ways to look at this. You can look at it that we're going to form crystals of A just because that's the region that we're intersecting, melt plus A. Another more logical way to think about it is we've got mostly A. We've got 80% of A if we've got 20% of B. So it's more likely that it will be A crystals that form. If we wanted to know the temperature that the crystals formed at, we would, I lost that cursor again, we would construct a horizontal line over to the temperature axis. We would measure the distance between 1300 and 1400, and then we would measure the distance between 1300 and that horizontal line. We'd divide the second one by the first one, multiply by 100, and add it to 1300. All right, let's continue on with this problem. Whenever you see me wiggle the cursor like that, it means that on my screen I can't see it. All right, oh gosh, there it goes again. All right, now I'm going to cool it down a little bit further. I've cooled it down to point L. To get the temperature, I make a horizontal line over to the axis. To find the composition of the melt, remember the composition of the melt has changed. The reason it's changed is because now we've got a whole bunch of crystals of A. So we've pulled A out of this. Obviously, we've enriched the melt in B. to find the composition of the melt, we make a vertical line and we read the amount off the numbers on the bottom, or preferably we do that measurement of A to the line, divide the second one by the first one, and we will get the percent of B. It looks like, oh, it should be about 36% in this particular sample. Now, there's something else we can do at this point. We've got crystals and we've got melt. And one thing we might want to know is what percentage of the system is crystal and what percentage is melt. Well, to do that, we look at this line, which is called a tie line. And we use that lever rule again. We measure T2L. We measure ZL. ZL divided by T2L gives us the percent of solid. If we measured T2Z and divided it by T2L, we would get the percentage of liquid. Okay, we can continue on this from point L. From point L, we can continue down to the eutectic. The eutectic is marked by two aspects. First of all, it's the lowest temperature that the liquidus hits. It's also the point on the diagram where you can get the most phases present. In this case, you can get solid crystals of A, solid crystals of B, and melt, all at the same temperature. When you get to the eutectic, for the first time you can get crystals of B. The crystals of B and the crystals of A will form at the same rate. The reason is that this particular eutectic is right over the 50% mark. In other words, the melt at this point is 50% A and 50% B. So you're going to get your crystals forming in a 1-to-1 ratio. You move ultimately to this the composition line that you started with. If you let the whole system go to equilibrium, you have to end up with what you started with. If you ended up with 20%, if you started with 20% Z, you have to end up with 20% Z. And that's the end of the show. Hopefully, this was helpful for you.